Okay, so we've taken a look at water gems, and you can continue to poke around with that for a bit while I get the notes ready. But what we're going to do today is talk more about channel flow, and I've got an example to show you that you're going to need for the next homework assignment. And speaking of which, here's the handout that's referred to up on the screen as the cover sheet for the next homework assignment. Basically, if you haven't already digitized the demand estimation curve, I'd like you to do that. March 8th is when you'll need to do your first submission for type sizing and optimization, and that will be the bulk of what you need to have ready for submission that day is a pair of maps, your network at maximum flow and at very low flow, and it should be annotated with diameters, flow rates, pressures, and so forth as described in the handout. The next homework assignment's due on Monday the 4th of March, so that is next Monday. And I want to talk first of all about energy. In the last class we talked about the starting point for open channel flows considering both energy and momentum. And so let's first talk in terms of energy. We've got some prismatic channel. It's a rectangular cross section, and we know at location 1 the riverbed is some distance above the horizontal datum. The width of the channel is known, and we know the average cross-sectional velocity is 0.55 meters per second. And so if we know the total energy is 1.41, can we use that to find the depth of flow at 1? And then also, what's the flow rate? Okay, so remember that total energy is the depth, the velocity head, and the elevation above the datum. And for our energy equals E1 is 1.451 meters, and the elevation at 1 is known to be 0.782 meters. Then we're trying to find Y1, the depth of flow at location 1. So it'll be the energy at 1 minus the velocity head minus the elevation above the datum. All right, 1.451 meters minus the velocity head minus elevation above the datum. So the depth of flow must be 0.654 meters. And we can use that to find the flow rate because Q equals AV, and the area is going to be dependent on the depth. The width of the channel is 0.5 meters, 0.5 meters, and the depth is 0.654 meters. Okay, so the flow rate will be the area, 0.654 meters times the 0.5 meter width times 0.55 meters per second is the velocity. So the flow rate is 0.180 meters cubed per second. We're going to use principles of energy like this when we try and predict the hydraulic jump. The hydraulic jump is what happens in that flume when water flows under a gate at a velocity faster than it really should be going under steady, uniform conditions. So we're going to have hydraulic jump day later in the semester and try and predict what the different depths are that the hydraulic jump will go up to. And all those calculations depend on us calculating energy at different points. And energy is the sum of the flow depth, velocity head, and elevation above some datum. These are really the main equations that we're going to use for the rest of the semester. In the sense, you don't even need an equation packet because you could memorize these equations pretty easily. Particularly because we're not going to use Darcy-Weisbach hardly at all. It'll just be continuity, the Manning equation, and the energy equation. And with those three, we're going to be able to understand phenomena like the changing channel width, the hydraulic jump, and a lot of things in between. Here are some typical n values for different material types when used in the Manning equation. The friction factor n doesn't take into account variations in flow conditions, but sometimes tables will have different n values depending on the slope. And so it's not a direct accounting for flow conditions, but sometimes indirectly it's accounted for by using a different n. And so I'd like you to try out the Manning's equation with this example that's just been revealed in the box there. What's the flow capacity of a rectangular channel at 1% slope? So the channel is 3 meters wide, and we intend for it to be 1 meter deep, and the slope of the channel bed is 0.01. That's how we put it into the Manning's equation. And so, what is the flow rate capacity in this case? Did everybody get a copy of the notes and the homework? What to choose for the n value is often the hardest part because it involves some subjective judgment. In this case, it says it's smooth concrete, and so maybe that's a hint that the n value we select should be on the smaller end of things. What I used was the 0.011. as the N value for smooth concrete. But it's reasonable to use a value higher than that and say the capacity is going to be a little bit less. If you want to be conservative and you're trying to predict how much water it can convey, this is going to be a best case scenario since I've chosen the smoothest concrete value. .4 cubic meters per second is what this channel could handle. What if it was a 3? First of all, are there any questions about this part? It's the first one that we've done already. All right. Well, this is a 1x3 channel. What if it was 3x1 in terms of 3 vertical, 1 horizontal? And in this case, the area is still 3 meters squared, but the wetted perimeter has changed, right? We've got more wetted perimeter now. We've got 3, 4, and another 3. So the wetted perimeter is 7 meters. So the hydraulic radius is going to be 3 meters squared divided by 7 meters. I haven't got my calculator. What is it? 0.43 meters. All right. So how would the capacity change? Do you think that the capacity is going to be higher, lower, the same? Lower. Well, what's your argument for that?
The hydraulic radius will be smaller. They're going to take it to the 2/3.
All right.
And the velocity will be lower.
Hydraulic radius is smaller because, well, it is smaller. And the smaller value to the 2/3 is going to be smaller than it was when it was 0.6. All right. What about from a physical standpoint? Well, what's the physical argument? Just equation aside, think about the way water flows through channels. Now, how is it different?
There's more contact with the surface, so you have more friction.
There's more contact with the surface, more friction. So let's see, let's quantify what the effect of that will be. It's still 3 square meters of surface area, and we're still using 0.011 for concrete. But if we now have this different hydraulic radius, and the original slope of 1%, what's the capacity of a 1x3 channel if it's tall?
15.5.
15.5 cubic meters per second. That's a significant reduction in capacity. There is something that's called the best hydraulic section. And we'll get into that in a future lecture, like these perfect shapes that have the optimal blend of minimizing the wetted perimeter. You know, like for a certain cross-sectional area, there is a shape that can minimize the wetted perimeter. And whether it's a trapezoidal channel or triangular or circular, certain cross-sectional shapes that are optimal for design. And since you have any number of combinations that can convey a certain flow rate, what would you do if it's a 30 cubic meters per second? So pick any combination of depth and width that will give you 30 cubic meters per second. So what I'd like you to do is, in design, you can have some bottom width B, some depth Y. What we want is, let's still assume the slope is 0.01, and we'll still assume that the roughness is 0.011. And so what should the geometry of that channel look like in order to convey Q is now 30 cubic meters per second? you're not sure how to get started, probably the simplest approach is just to select some width of the channel or some depth that you'd like to have, and then find out what the other parameter will be. Make an assumption of what you'd like to have.
2.
Okay, of course, Excel can be used in design problems. You can do solver where if you wanted to pick any particular width, like for example, if we said that we know we want to have a 1 meter depth, then what should be the width that we're going to use for our design? So if now we're supposed to be getting 30 cubic meters per second and we're only getting 19.4, we're going to have to make the channel wider for a depth of 1. So how wide would the channel have to be in order to accommodate it? So in this case, we can set up a what-if analysis that does goal seek, where we're trying to get this equal to the 30 that we know of, and the parameter that should be changed is the width, and it'll automatically solve for the width that's needed. 4.26 would be the width in this case. Excel, obviously, you can use for any different set of combinations. What are some of the depths that you design for? What are some?
2.06.
So did you start by picking a B or picking a depth?
I made it a square, turned A into X squared and R.
Ah, okay. So you made it a square. So if it was a square, then you said that
R is 1/3 X.
B is going to be equal to Y, basically, right? There's going to be some depth Y.
Yeah.
All right. So B and Y were the same thing. Good. And so you said, what was the result of that, resulting depth?
2.06.
2.06 for both. All right. 30. Good. Jordan, what did you pick for your dimensions of the channel?
I didn't even get that far.
Didn't get that far?
No. I tried to, what I did was, I set up the equation, I tried to solve for A instead of picking
Mm-hmm.
A or Y. And it didn't work out.
Yeah. And I'm sure, as you recognize, the challenge for solving for A is that it's a function of both B and Y, and both of those variables are also in the hydraulic radius. Right. So it's tough. You have to start by just basically assuming one of them. Okay, well, that's all for today. Just remember, if we look back at these announcements, that the homework assignment, this first open channel assignment, is due on Monday. And then the Friday following that, your first stab at the type sizing estimation will be due.
That's a week and a half.
From today, yeah, week and a half from today. Yep.
Are we going to be getting like our demand estimation on board?
My hope is to get you your demand estimations back on Monday.